The ultraviolet catastrophe was a prediction made by classical physicists in the late 19th and early 20th century. At the time, it was known that objects would begin to emit visible light as they became hotter. According to this prediction, which considered light as only a wave, an ideal black body will eventually emit radiation of infinite intensity. The resulting infinitely intense light of the electromagnetic spectrum would, in theory, cause a catastrophe. In this video, we will show a simple experiment of real blackbody radiation using a light bulb. Here is the light bulb and the power source that has a knob which can be used to adjust the power or voltage. As we turn up the voltage, we are giving more thermal energy to the tungsten filament, which we will define as our system. The filament has to do something with the energy that is being put into it by the voltage, so it emits both heat, which leaves the system, and converts some of the energy to light, which also leaves the system, and we can see it if it is in the visible region. The filament of the light bulb, which is very close to the center of the screen, is getting hotter and starting to glow. As we increase the voltage by turning the knob on the power supply, the light becomes more intense. This is exactly what we want the light bulb to do, give us light. This phenomenon is called blackbody radiation. Every object that has a finite temperature is always radiating energy. This includes the sun, the earth, our bodies, everything. But what do you know about substances that give off a lot of light? Often these objects are hot, so hotter objects are giving off more light than cooler objects. In other words, a hotter object gives off more intense light than a colder object. But what's surprising is that as an object gets hotter, it starts to have a peak intensity at relatively lower wavelengths of light. Most cold black objects are actually emitting light in a region of the electromagnetic spectrum that we can't see. You have probably observed this with a piece of coal or the burner of an electric cooking range. It begins as something that is black, but as it gets hot, it begins to glow red, which is a relatively long wavelength of visible light. The intensity of the light goes back down as he turns the voltage from the power supply back down to 0 voltage. The filament of the light bulb is still emitting light even when it looks dark to our naked eye. As the temperature of the filament goes down, the light it is emitting is in a wavelength range that we cannot detect with our eyes. Next, Dr. Lyle is putting the light from the glowing light bulb filament through a diffraction grating to see which colors can be separated out from the light as he turns up the voltage on the light bulb power supply. We need to have enough energy going into the bulb for the electrons within the tungsten filament to make the transitions between the allowed orbital energy levels of the material to the excited state. When they decay back to the ground state, light is emitted. You can see the spectra begin to form on either side of the bulb as it starts to glow. Initially, we see red and green light, which becomes brighter as the intensity of the light from the bulb increases. This initial light that can be observed through the grating is mostly red in color, indicating a wavelength of 620 to 750 nanometers. As the bulb gets brighter, the spectrum we are observing becomes more intense, and it does broaden somewhat to give green and blue light. But we continue to see red light emitted in a more and more intense fashion. With a better diffraction grating, we would be able to see more colors between the red, green, and blue. What doesn't happen in this experiment is that the light doesn't change from red to orange to yellow to green through blue and purple. It doesn't cause the catastrophe of light at infinite intensity, which would be predicted if light was only a wave. is a graph of spectral radiance, which is a measure of the energy or intensity of the light emitted as a function of the wavelength of the light. Here we've compared the prediction of Planck's theory, which is in the red, green, and blue curves, to the prediction of classical theory, which considered only light to be a wave. We can see that the classical theory predicts that at 5,000 Kelvin, we have infinitely intense light. However, our sun, which has a temperature just above 5,000 degrees Kelvin, actually has a spectrum that looks more like what we see with the blue curve. This is better predicted by Planck's theory. Please watch the video lecture on the wave-particle duality of light to learn more about the equation that governs this phenomenon.